Okay. Now this is very standard. That's a free lab. Some teachers also do it. Free lab. No, some do. So if you go to 1A and B, that means you're free lab every lab. It varies from, but mine is pretty universal. Basically, you want you to be organized and prepare for that lab. So you take the reasons, so you spend time. Okay, so also there's a new department requirement to handle lab. There's the that can really be important to sometimes handling okay. Some of these machines are long. How do you do this? 2.00 milliliters so all three labs when you turn the lab in electronic, can be put in three labs. So all labs have title. All labs have a purpose or goal. So free lab is very easy to do. It counts for 30% of the grade of your lab. So everyone should get a 30% bonus. But this it doesn't require any thinking. It's a matter of what's the purpose, what's the title, what's the procedure, and then any also first aid. Now this first lab we're doing is very, very, very safe. We're using water. Now there's a first aid sheet on water, because if you get too much of it, it's very unhealthy. If you don't get enough of it, it's very healthy. So you need just the right amount. But no first aid on water. The chemical name is like hydrogen monoxide. And there is one available if you look it up. Done by a high school student down in Southern California. Okay. Sometimes there are pre-lab questions, sometimes there aren't. If there are pre-lab questions, answer. Basically, the pre-lab questions get you into the procedure, so you can study the procedure better. Then there's the actual procedure itself. That's your ticket to do this lab. You don't have that done except for this lab, since this is the first one. You don't have that done, you cannot do the lab for safety. It's like coming with flip-flops. For safety reasons, not do the lab. Okay. Now the data table, you're gonna have to do a data table anyway, so you might as well do it for the pre-lab goes. Sometimes there's a data table part of lab in your lab packet. A lot of people just cut that out and tape it into their lab. Yes. Okay. Yeah. Your lab book can be a composition book. It can be some graph paper in there. Some of them come with a fancy cover. Some are leather bound, and you can get all ranges of lab book. Now that's not the same thing as the packet you find. Two different things. Okay. All right. When you're in lab, you're doing calculations. You're gonna have to post lab questions. You're gonna write a conclusion. All labs require a conclusion. Now, sometimes it says write a conclusion, sometimes it doesn't. all labs require completely. You can see it's worth 30%. I'm not asking for a book. I'm asking for a paragraph. That's all. Just kind of bring it all together. He has some issues. Experimentally, mention that in the conclusion as well. Okay, so let's look now. Now, what I have up here is lab 3. So it's this one is easy to find the purpose because it says what it is. Sometimes you have to read the back, figure out what the purpose of the lab is. Okay, but you need a purpose, because why are we doing this thing? I know it's for fun. Why are we doing this lab? Now, this lab, we need to understand the concept of density, the very important parameter on any kind of material. For example, during the gold rush, there's a substance called iron pyrite that looks exactly like gold. Exactly. Same color, shiny, and it's found around quartz. So when the miners came in with their material, the first thing the person that checked against the gold density is very different than gold iron carbide. Very different density. Iron carbide is extremely cheap. Extremely cheap. Gold, as you know, no. So that's one really nice application of density. But all material property density. Yes, not over volume. In our case, it's going to be grams over millimeters. There's a giant reference book in the lab. This thing. So, century business. When I was a sophomore, I had to buy one. Now you can get a digital. I had to buy one in the 60s days. All kinds of chemical documents, chemical women, conversion back. Okay, so density is really important. So you're going to be looking at different ways of measuring density in today's lab. Something that's very dense is thick. Something that's not very dense is light. You pick something up and compare it. One's heavier than the other, it's denser, assuming the volume is the same. The volume is different. No. Paper is not very dense, but if you pick up a whole bunch of it, it's heavy. The volume. Okay, but this is a typical machine. Obtain an unknown block in the metric form. This first one here, what you're going to be doing is going to be measuring a cubic block and calculating its volume. Then you're going to weigh it. You're going to have mass over volume. You're going to divide by the volume because we want it in 1 millimeter. We want grams per 1 millimeter. So you see, measure your length, width, thickness, the block, the metric ruler, record it in your data table. So that means you're going to need a place to put these measurements. Now, sometimes they include a data table, and sometimes they don't. Now, the problem with this lab the way it's written, I did not write this lab. When I write labs, I always include a data table. You cut it out or copy it what you need. But whatever you do, if there's anything on the record, you need to have a place for that. Whatever you're recording, whether it be a measurement, an observation, whatever, that needs to have a place. Sometimes the data table is the calculation. Calculations are based on previous data that you collected. For example, on the cube, width, height, length. That would be the data in that cube. The calculation is going to be calculating the density. First calculation is you calculate the volume. Next calculation is you measure the mass of it. And the next thing is that then you do the calculation of dividing the volume into the mass. Again, normally you have a data table rather than the way this is set up. Frequently there are, always there are post-lab questions. Those are be done at home or in your study group. Whatever you like to do. Normally we work in teams of 2, but you're going to turn in an individual lab report. Just your name. The data is going to be the same. We can work together on it, but I need to have individual labs. So when you submit it, you have to upload it. And it's uploaded to your name, not your team's. And then lastly, this one does not say write a conclusion. But every lab needs a conclusion. This pre-lab is lab write-up is very similar when you get into 1A and 1B, or 2A and 2B. Almost every place I've been worked at, I've had very similar to this. So this is a good time to get comfortable with pre-lab. Now they're not to be done during lecture. They're to be done at home or before. Okay. As I said before, conclusions are what did you learn? That goes back to the purpose. What I need to do is sum it up. If any issues came up, again, mention those. I dropped the cube of wood into the toilet or whatever. Or it got it wet. Now it's massive difference to the wet. Whatever. Any kind of issues that come up, that goes in the conclusion. Now the way I grade this, I read your conclusion. And if it's reasonable, fine. If you had issues, when I look at what the issues were and how that affected your data and how you treated your data, what was supposed to be. And I agree reasonably easy. This, in my opinion, are easy points, lab points, but you got to do them though. Easy points, this lab is worth 20 points. That's the same as 20 test points. If you blow this one, it's just like missing a bunch of problems on your test. So keep that in mind. You're doing this. Think of it as an investment. Now, it depends on your instructor how big a point value they assign. This is about what most instructors do: 20, 15, 30 points in that range. Well, at Sac City, I would 3 labs, and every instructor there has 20 points, which is 20 points is handy for labs. All right, so any questions about the lab write-up? Yeah. Yeah. One your handwriting. You can have a data table that expect up to no. Sometimes data tables last. Most of that yeah, the whole thing. And the reason the part I did that is because when you're doing electronic, the purpose purpose of the pre-run, we don't think the last 40 years. But handwriting, everyone. It's very sexy. Yeah. When you submit it, when you scan it. Yeah. You notice like to make it copy of the place that you would run it. So I'm going to see what's to do that and then what's right. No. Handwriting, don't do both. It's handwriting. So you should be writing. Not the background. Main final purpose. To not the back. Yeah. Point the problem inside of the wall.
Not only were writing or for example,
so are you going to be on you need to buy it now. This is just electronic copy of the pack. So you need to buy it by the right. You're not wrong. Because that's the thing. Right, well, these are the lab one of them they were up. I'm going to if you go to the that's why you need to buy it. That's why I'm wanting to do because the book comes out of it. When you want to tell them, you buy it. You can do it. That's why I'm doing it. Not wanting to. Makes sense? Yeah. So what you want to do is I'll show you how to do that as well. I'm trying to tell you otherwise. Next week, sand and salt mixture. Figure out sand is much easier. You can say the salt. Now this is very much. Okay. Not necessarily remember now, question, I have a blow right up there. Number one, number two, I'm always, you know what? When I hear you, so speak up. That. All right. So someone sent me an email to remind me to post an example. And I have, again, they go to the same place. They go to Outlook. You do it in Canvas, it comes to be an Outlook. If you right, either way, whatever's convenient for you. Because I get Canvas stuff all the time. In fact, most of the time. And look, by the way, let me mention a couple things. In Canvas, as you all know, there's the ability to send a message. Is when you try that, sometimes people feel like it's simple. You gotta send me something to be effective. Open up. Whatever your fine. Okay. Otherwise, this is the way you can see it. All right, let's take it. Now, we talked last time about periodic table. We talked about different kinds of ions, two kinds, negative ones, positive, cation. Then there's it has to do with balancing the number of electrons and the number of protons. If they're out of balance, this is all on the so election. If the protons and electrons are out of balance, you have a net charge on that atom. Okay, so I want to talk about what the actual reaction looks like when something loses or gains an electron. First of all, What is a reaction? Chemical change, yes. Okay, so. All reactions, no exception. Start with reactants. And the conditions are favorable, turns into the product. Only if the conditions are favorable. If they're not favorable, nothing happens. You just have reaction. No problem. This is the way inorganic, organic, nuclear, biochemistry, we all work this way. All of them. Well, biochemistry, because biologists are in charge, they have different names, and like instead of reactants, they call it substrate, but it's just like a reactant. Okay. So the products have to be more stable than the reactants. Otherwise, it's not going to happen. All the time. All atoms, potential energy built into. You also have kinetic energy built in. Kinetic energy is motion. Potential energy is in the bottom. That's where the potential energy is stored. Okay, total energy is the sum of potential and kinetic energy. Now, who knows how we measure kinetic energy of an atom? Yeah. Temperature, right. So the metric for kinetic energy is going to be temperature. And that's going to be Celsius. Centigrade. Higher the temperature, more kinetic energy, more motion. Everything is moving. This here is moving. When I'm stepping on it, moving. Even though this appears like nothing happening, moving. So as the temperature goes down, the movement goes down until we reach no movement. And that's called absolute zero. That's the only time something's not moving. And it's really cold. It's minus 273 degrees Celsius. Minus 273. Huh? Then, where is space? Close to the sun, freaking hot. If you're not close to the sun, it's freaking cold. No, it's really hard to get that. Physicists do it, but it's tremendous amount of energy pull out, slowly. Okay. When we're talking about absolute temperatures, we use Kelvin instead of centigrade. Notice I haven't mentioned Fahrenheit. Fahrenheit also has an absolute zero. It's mentioned, well, range two, I'm just saying that Fahrenheit is counterpart as well. Fahrenheit, centigrade, both get on absolute zero. Just the units are different. Fahrenheit. Okay. All right. Let's go back to this reaction stuff now. What the potential energy of the reactants and products? Notice the product at a lower potential energy. Not all the time, 99% of the time. Well, what happens then if the temperature of the surrounding doesn't change? When we have a total energy, potential and kinetic energy, initial potential and kinetic energy, final, and they're the same. But they lose potential energy, it's converted to the other kinetic energy. So usually when this happens, and what's kinetic energy again? Heat. So the reaction gets hot whenever we lose potential energy. But the products are going to be more stable. Otherwise, it doesn't happen. Now notice there's a hump there and reactants to products. Because to go from reactants to products, we've got to break bonds. Requires energy. For example, if you have a piece of wood, why doesn't it spontaneously start on fire? Yeah, you gotta supply energy to it. And then it supplies itself. But to get it going, you gotta go to that pump. The bigger the pump, the more energy you have to put in. There's all kinds of fancy words for that. Activation, usually, blah, 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 blah. The main thing is to remember though, is a hump there. And the hump represents breaking bond. So when you start a reaction, you got to break bonds, it takes energy to do that. And then if the reformed bonds are more stable, that's potential energy to form. If they're not, they won't. So that conflict, what's breaking those bonds and then activate them. And let me see if you have to put that. For example, you have gasoline and wood. Gasoline's a lot easier to get going than wood, so its activation energy of the pump is smaller. This formica probably has a really high activation. You have to take a lighter here and burn this for a while, and that's not going to do anything. And then put a little black, that's about it. Yeah. Yeah, flammability issue is the activation. In fact, there's something called example, rag is salt and stuff like this. And during the summer, it can self well. Not heat, just part of that. Actually store them high. Not even. That's why you should always store oily rag. You can solve in some kind of frozen food. You can sell. This activation is really low. Flammability, something that's very flammable, low activation, something that's not. For example, sort of diamonds. What are diamonds made of? Parts. Charcoal. Charcoal, yeah. Yeah. Yes, which was problem. The activation is really, really hard. Hard to get activation. Energy. I'm in trouble. Yeah, this would be where charcoal is. So when the bonds that keep those carbons together in diamonds have higher potential energy than the bonds like a charcoal. Okay, so knowing that background, we have reactants and products, all reactive. There are no products, there's no chemical reaction. Difference between what potential energy you start with, potential energy you end with, and that's stored in the bonds, is given off in kinetic energy, which is heat, measured in calories, joules, or whatever it's measured. Okay, so let's look at some reaction stuff. All right, so this would be the reactants, products. Okay, so we're having fluorine. Fluorine likes to gain electrons. And when we gain electrons, it's going to be on the left side. So the electron is going to merge with the reactant fluorine, merge together, and they're going to form a new ion. The anion is negative. Okay, so products are always written on the right, reactants are always on the left. If we have something coming together on the left, you're going to be combining. They could also split off. I'll show you one of those in a minute. Okay, so fluorine starts with it's going to have 10. 1 plus no. So you have 1 more electron. Go to a prior example. Now here we have lithium giving off an electron. Split off from the lithium. That means we have one less electron. The lithium, the atomic number is 3. You lose an electron and you want to have 2. Protons, 2 protons, 2 electrons, and then the net positive charge. So that ion is a cation. So we have reactants, products. One reactant, 2 products. Lithium plus 1 is more stable than lithium by itself. Fluorine is more, fluorine ion is more stable than fluorine by itself. That's why that happens. Okay. It always happens, the product is more stable than the start with. Always. I'm going to drive this home in this spot. Stability rules. Stability rules. It doesn't become more stable, it won't happen. It has to do with the potential energy that you start with, that you end with. Now, whenever we have anything going on, in the situation when lithium is given off an electron, you can't just let it go into what's called beta radiation. Beta radiation isn't normal. So what happens, you have to have a recipient to that electron. So that's why some things are paired really well together. One gives off an electron, the other receives one. One gives off 2 electrons, the other receives. You have to have a donor and a recipient. Involving electrons moving from the reactants. Always. You can't have a bare electron. Okay. Now, go back to the periodic table. Group 1, likes giving away electrons. The stability reasons I'm talking about. Why? Right now, group 1 likes to lose 1 electron. Hence, it likes to form a +1 atom. Group 2 likes to lose 2. Form a +2 atom. And over here, C 7. 7, C1, this is -1, and -2 now, -2. And over here, pretty nice, right here, there's no ion. Because it's either going to lose 4 or gain 4. And what happens, it does neither. That's a group carbon. The group carbon doesn't form ions easily. It does form an ion that's very unstable. So everything forms ions except group 4 and group 8. Group 8 are the inert gases. They don't do anything. Okay, so that's important to know as part of the organization of your activity. 4 groups I wanted you to memorize. There's the alkali metals, earth metals, halogens, and red gas. Okay. Ionic compounds. There's 2 ways to describe an ionic compound. One way is to have the metal and you have a non-metal. The metal like to be away electron. Non-metal like to be speeding. So the non-metal. Can you what? Or another that iron in the middle. Down in the middle, and iron in the middle. Both of those mini. Fucking no. No, and pronoun is and I don't. Pronoun is really important. Okay, this is what they're talking about here. Now, all of you heard of isotope. That's a radioactive isotope. Right? What is the matter? This one is gonna be. All right, nice. Well, since from. An isotope. Same number of protons. Different number of neutrons. Yeah. Yes. You experiments with it, they act exactly the same. There are a few exceptions to that. There are actually the exceptions come into play in the math. The technical mass spectrometry that can measure the different mass, including the neutron. So then, the neutron 21 and neutron 20 would act as that's the most common instrument that uses differences in that. But as far as chemistry goes, let's say carbon 14, 12, no problem. Now the problem is if one is radioactive and the other is not, and your body thinks they're the same thing, that's going to be a problem. It's like strontium, it's calcium, iodine, all those can become very radioactive in a radiation incident, like Chernobyl, atomic bomb, something like that. And your body thinks it's plain old item. It's not. It brings into your thyroid and you get the cancer. Because chemistry is the same. That's the bottom line. Chemistry is the same. Now, when we look at the atomic mass, the decimal number in periodic table, it's a mixture of isotope. That's a good question. Okay, so let's look at um, we look at say there's carbon here. If you look at periodic table carbon, at 12.01, that's because carbon 12 makes up almost 99% of our carbon 13 makes up 1%, carbon 14 is 1. So these are heavier than carbon 12. So because there's so few of them, it doesn't bring the average up. Or the average is close to the 12, and you can tell the basis of this. How do you tell it next thing? The stability rule. If there's more of them, that means it's more stable. First, I mean, significantly less. In fact, there's a lot of little shenanigans going on in the world from birth. Carbon 14 is carbon 12. All these little nuclear chemistry stuff, you know, all the time, 24/7, 365. Now look at chlorine. Chlorine, 20%. Chlorine 19. You know what it is. That must mean that fluorine 20, fluorine 18, all those others are really, really unstable. 100% fluorine and 19 make it tremendously stable. This concept of stability makes sense. No one looks more stable. Now, let's look at boron. Okay, boron 10. The decimal number is in 2 years. Grams and in atomic mass unit. Talking about numbers, we're talking about chemistry, the way we stuff is we're using a gram. This is gram or okay, so this said for maybe this one. When we take those percentages, that's enough. That's what we can get. We put the one with the then we'll do the next. That's how we get the decimal number. That's when you get the percent of the isotope. This is called a weighted average. Out of the weighted average, you take the percent of the isotope runs net. When it's net, that goes together, and that's the this one that you find. Have a weighted. And the weighted part comes in, we're talking about not everything is treated equal. There's a percentage involved. And that's the weighted part. So every one of these, you can do the same calculation. You do the lithium, that'd be 742% times 6015 plus 92.58% times 7016. Add those together, you'll get. Okay, that makes sense. It has to do with the natural abundance. Really what that means is the relative stability. Stable from what? Stable was stability again. Now the decimal number is called an atomic number. And this here, what we just did. Convert percent of fraction times mass today. Again, it can either be grams or AMUs, atomic mass units. This is just what we just did. And you have to know how to do that. Okay, so that's chapter 4. And there's a lot in this chapter. There's a lot. Probably the trickiest thing is this weighted average. And we're going to start a week from today. No. Are there any questions about this weighted average? Now, regarding the testament, bring your finished statement down. You shape that, not the especially in the on the minimalized test and revise. One that stress, all set, so just relax, study the same kind of material. Do well. There is no questions. All good for you. That would be if but you start with the work problem, you make sure you set up. And then you follow your logic. And you follow your logic, you have no longer making the word. And page 3 of that, which is the same one as on last week. But very similar. Yeah, I mean. Yeah. No. Who will you get this? This has to be. No. I think same thing with diversity. Same diversity that we have to. We want. For the final. Whatever we do. For the word, you want to continue down. We find it.
We don't have to.
That's been fun. Because when you do it on your part, that's when you can get this. I always find it fun. Thank you. Okay, now, first here on one of the now, here we have to come to. Second, the meeting there today. And now, is free to choose that.
safer, feeling.